Welcome everyone to the class number 4. Sorry for the delay. We had a little bit of a technical hiccup. Evan is currently in Mexico and Brad is off doing what Brad does. So welcome back. For those of you that are still with us after last week's class, hats off and congratulations to you. Security models are bone dry as a desert without any water or hope for salvation. But we really want to give Brad a round of applause, if you will, because he did a great job in presenting that terribly dry topic. So I hope you guys all remembered. I also want to give a shout out to all of our moderators that are with us tonight. Lori, Mike, Chad, really appreciate you guys being here. Charles. So, hats off to your moderators, tip your moderators. They'll be here all night. I'm going to take you through the fourth class of the 2021 CISSP Mentor Program. You guys haven't probably seen or heard from me yet, so I'll do a quick introduction. I'm Ryan Cloutier, the one that keeps getting blamed for stuff. I am the Principal Security Consultant for Security Studio, and I'm super jacked to be here tonight to take you guys through this. We're going to cover some really fun stuff. Some of it might be things you've heard before. Some of it's going to be stuff you've never heard before. We're going to do some basic housekeeping here, and then we're going to start rocking and rolling. But before I do that, I do have a security joke for you to keep with the theme. And that is, what do you call a pyramid that has been excavated? It has been unencrypted. Ba-dum-bum. All right, moving on. So matter of housekeeping here, we want to go ahead and keep that chat respectful. Just a reminder. Respectful chat only, no religious talk, no political talk, no inciting of violence or anything involving current events that are going to get people excited. Just keep it to the mentorship program, the CISSP, and edifying each other. So just a quick reminder, be adults, please. And thank you for doing that. So let's dive right in. So we've gone through chapters 1, 2, and 3, and we're part of the way into chapter 4. So how many of you have had a chance to read chapters 1, 2, and 3? And if you guys have questions, definitely fire them into the chat. The moderators are going to be happy to answer those. Moderators, so I am monitoring the chat on one of the many monitors on my wall. So I will be keeping an eye on that. If you guys see me looking up, I'm not rolling my eyes. I'm looking at my other monitors. So only 112 slides tonight. We're going to get through this together. And before we dive too deep, I want to cover something that is really effective, something I personally used when I was studying for this exam. And that is these study tips: to study in small amounts frequently, no more than 20 to 30 minutes at a time. As you can imagine, you're busy living life and you're trying to digest all this crazy information. And to make matters worse, a lot of this information we tell you that you have to memorize, but you won't actually need or use in your career. So that can make it a little more challenging. And tonight I'm going to tell you some of those same things. And I'm going to move a little quick, but just know that when we say to memorize it, it really is go back and memorize it. I encourage you guys, if at any point I'm moving too quick or any of the instructors are moving too quick through the material, keep up with it as best as you can, but then go back and watch it, put it on slow-mo, whatever you need to do, pause a frame, but make sure that you're actually taking time to really memorize this stuff. Use a flashcard app. A flashcard app was my greatest way to study this. I was able to, in all this downtime that I had, now this is in the before time, where we actually went places and stood in line and did things like that. I would use my flashcard app anytime I had downtime and just a few minutes of study. I did this for probably about a year, and I was able to successfully pass the exam without a problem. The other bit of advice I'm going to give you is to take naps after heavy topics. And this isn't the kind of nap that comes on from reading the material and falling asleep, but this is after you learn something new or heavy, or dry, try to get in a quick cat nap. This is something we learned from Albert Einstein. He liked to sleep in non-traditional segments. So he'd do these like little 20-minute power naps throughout the day. And I can assure you personally, that does help to retain information. The other thing that's going to help you a lot is writing things down and then saying them out loud. This is the same thing, by the way, that I teach when it comes to security awareness training. Read that scammy email out loud and you're less likely to fall victim. Well, when you're studying, if you write it down and read it aloud, you've actually reinforced it in two different parts of your brain. Leverage the study group. It is a good thing to do. Lots of great people in there. I've been watching it for the last couple of weeks here, and I've seen a lot of amazing activity, a lot of really cool suggestions, study tips and tricks, and just networking in general. So continue to do that. And lastly, take a break, get up, get some fresh air. It's amazing how a 5-minute stretch outside with a lung full of fresh air does for you to recharge you, recoup you, and get you ready for another study session. Here is the updated link to the study group. I know we had some challenges with that last week, and of course the practice test FRSecure. And we really appreciate FRSecure and just want to give a shout out to those guys. So far we've gone through the introduction, and we heard from Evan, his viewpoints and visions on information security. Fascinating stuff. If you don't remember much of it, maybe at some point go back and listen again. There's little nuggets of wisdom hidden in there. We went through domain 1, security and risk management. We went through domain 2, asset security, and now we are in domain 3 on our way to domain 4. So with that, let's do a brief recap. So quiz time, pop quiz. Hey, what type of memory is often used for CPU registers? Is it A, DRAM, B, firmware, C, ROM, or D, SRAM? Give you guys a chance to put your answers in the YouTube chat there. The correct answer is SRAM. So that would be D. What was ISO 17799 renamed as? Was it BS 7799-1? Was it ISO 27000? Was it ISO 27001? Or was it ISO 27002? Again, put your answers in the chat. It was ISO 27002, and BS stands for British Standards Not Bull, you know what. So number 3 here, which of the following describes a duty of the data owner? Is it to A, patch systems, B, report suspicious activity, C, ensure that their files are backed up, or D, ensure data has proper security labels? Now, if we think back to Monday's class, what is a data owner ultimately responsible for? Let you marinate for a second. They're responsible for making sure the data has its appropriate and proper security labels. Number 4, which control framework has 34 processes across 4 domains? Is it COSO? Is it COBIT? Is it ITIL? Or is it Octave? So if we remember, the key to this question is 34 processes across 4 domains. And I want to call this out for a second because the exam will test you in ways like this. Questions will be phrased this way. So this is important for you to remember. Look for the key information in the question. The answer here is COBIT. COBIT is the control framework with 34 processes across 4 domains. Question 5. Which managerial role is responsible for the actual computers that house data, including the security of hardware and software configurations? Is it A, custodian, B, data owner, C, mission owner, or D, system owner? It is the system owner. The system owner is ultimately responsible for keeping track of these hardware and software configurations. All right, quiz keeps trucking along. Number 6, what type of relatively expensive and fast memory uses small latches called flip-flops to store bits? Is it A, DRAM, B, EEPROM, C, SRAM, or D, SSD? If we remember back from Monday, it is SRAM or SRAM, however you want to pronounce it. let's see, a couple more quiz questions for you, and then we'll get into the fun stuff. Number 7 here is, what type of memory stores bits in small capacitors? Small capacitors being like small batteries. Is it DRAM? Is it EEPROM? Is it SRAM? Or is it SSD? It is DRAM. I don't have a picture here to show you, but feel free to Google it. All right, take a drink of water and we'll get you rocking on chapter 4. Just a quick check-in with everybody. Am I moving at an okay speed? If I'm going too fast, let the moderators know and they'll bring it to my attention. So we're going to be talking chapter 4, but domain 3, security engineering and the engineering and management of security. So we've covered security models from domain 3, and we've covered evaluation methods, certification, and accreditation. Tonight, we're going to cover secure system design concepts, secure hardware architecture, secure operating system and software architecture, virtualization and distributed computing, system vulnerabilities, threats, and countermeasures. I almost feel like these should be categories on Jeopardy. Alec, I'll take secure operating systems for 300. These were formerly separate domains: security architecture, cryptography, and physical security. They have kind of combined all that. It is going to take us 3 classes in total to get through this domain. So put your seatbelt on. This one's a little heavy. All right, so tonight we're going to start on page 116. If you guys are following along in the book. Let's talk about layering. Layering is such a critical concept to information and cybersecurity. The more layers that you have between the data and the human who's able to access that data, generally, the more secure you're able to keep that data. Layers are so important. We think of this in context of separating hardware from software. We think about this as isolating actions and activities so they don't affect the other layer. And if we're talking about the networking layers, OSI is a type of, is a good example of layering, and we will go into the OSI model and later on. A generic list of security architecture layers are the hardware, the kernel, the OS, and the application. But you can think of things like multi-factor authentication as an additional layer. We're not going to cover that tonight, but just to give you an idea, layering is a very important concept, and more layers are better. Abstraction. Now, this is a fun one. For those of you with a software development background, this is probably quite familiar to you. For those of you that maybe come from a hardware or networking background, this can be a little bit of a new learning, to kind of figure out what this means. But basically, it's that unnecessary details are hidden from the user. And the book has a great example. I'm not going to read it. You guys can read it. But basically, it simply means that you've abstracted away all the complexity. And we like to say that complexity is the enemy of security. That's a quote from Bruce Schneider. And what we do in security, if we're doing it well, we've abstracted a lot of things away from the user. So in this example, the user doesn't know all the things that go into making the MP3 file play music. They simply push the button and it plays music. So again, reminder, if it's in orange, you need to memorize it. So let's talk about secure system design concepts. So the ring model is still there, but basically it's using the CPU hardware to create layers to separate and protect the user mode from the kernel mode. So in this example, ring 0 is the kernel being the core of the operating system itself, the lowest level possible. Then the ring 1 is the operating system components. And this is the part that you're familiar with. You interact with ring 1. Most of us don't interact with the kernel unless we're like super hardcore Linux people and we're cooking our own kernels. So most of us operate in ring 1. Ring 2 are going to be those device drivers that you have to install to make your camera work, to make your speakers work, that type of thing. Ring 3 is going to be the user applications. Processes communicate between the rings via system calls. And system calls are generally slow when performing work within a single ring, but they do provide an additional layer of security. The ring model also provides for abstraction. Linux and Windows use rings 0 and 3 only. And a hypervisor mode allows virtual guests to operate in ring 0, operate in ring 0, 1 ring below, so ring -1. The important thing here is to understand that the rings allow you to have layers, the rings allow for separation, and processes are what communicate between the rings via system call. Little bit of humor for you. Back in my day, we had token rings and pagers. Different kind of ring, but I thought it was cute. Here's a visual concept of the ring, just in case all those words and descriptions I used didn't help paint the picture. So this is your kernel here, your device drivers, and then your application. And you can see it's colors coded from least to most privileged. We're going to talk about open and closed systems. So open systems use open hardware and standard components from various vendors. Pretty much every IBM compatible PC in the world is an open system. Closed systems use proprietary hardware and or software. So the one that we're most familiar with are the Apple products. Apple products are a closed system. PC products generally, if not in all cases, are an open system. So let's talk a little bit about the systems themselves. So this can be a bit of a hardware refresher for those of you with your A+. But let's talk about the system unit and the motherboard. So the system unit really is the computer case and everything contained within it. That would include your power supply and fans and all that fun stuff. The motherboard is a specific piece of hardware that typically, not always, but typically includes the CPU or central processing unit. That's the brains of the computer. Contains the memory slots, firmware, peripheral slots, such as PCI, PCIe. And these are peripheral component interconnect slots. This is how you like add a sound card, add a video card. And if I'm talking at a level a little bit low, it's because I don't know the audience's exposure. And I want to make sure we cover this in a way that makes sense for everyone. So if you're like, hey, man, I get all this, people here that may have not heard this except for today. So let's take a look at a computer. So, you know, they used to look like this. I don't know too many of us today that have machines that still look like this. I know I do, a lot of hardcore technology people do, but this is pretty much it. And you had your CD drive, you had your computer chip, your power supply, fan, video card, modem card. I think that's misspelled maybe, sound card, ribbon cables, so on and so forth. So this is just the basics of the insides of a computer. This is a little bit more of a detailed breakout look at a motherboard itself. So here you have the north bridge, here you have the south bridge. These help the CPU to route information to its appropriate places. We've got heat sinks because computers get hot, various jumpers, connectors, USB ports, ATA controllers, mounting holes, et cetera, et cetera. So if you're unfamiliar with the basics of computer hardware, I encourage you to spend a little bit of time familiarizing yourself with these components. If you're like, hey man, that's cool, where's the liquid cooling? Well, you probably don't need to study this part too hard. So the computer bus is the primary communication channel on a computer system, and it handles the communication between the CPU, memory, and the input-output devices, such as your keyboard, mouse, display. And all of that is happening inside the bus. So let's take a look at that. So remember, I pointed out that north bridge a moment ago and that south bridge a moment ago. So when the CPU gets a set of instructions, it's routing that through the bus to the memory. And in this case, the AGP out to the video controller. And then the PCI bus and the ISA bus here tie into the south bridge, which then connects to the disk, ATA or IDE, if you're still running older technology. So again, just familiarize yourself. None of this is in orange, so don't worry. But this is. So North Bridge and South Bridge, very important to know what these things are. And again, it helps the CPU connect to the RAM and the video memory. And the South Bridge is the I/O controller hub, or the ICH, and it's what allows your keyboard and mouse, CD drive, etc., to interface with the CPU. The central processing unit, this is the brains. It is capable of controlling and performing mathematical calculations. Anything a computer does at the end of the day is mathematical. and it is rated by the number of CPU cycles per second. So for example, a 2.4 gigahertz Pentium 4 CPU, and I don't even know if you could buy one of those, is 2.4 billion clock cycles per second. Modern processors today are running even higher volumes of clock cycles. And I won't go real long into quantum computing, but that's a whole nother concept. And you do need to know that it exists. And there is a little bit, tiny bit, like one little touch in the book about it. But just know that that's how the CPU is doing what it does. Everything has to be boiled back down to a math equation. Here's another example of what a CPU looks like if you were to remove it from its socket. So you have all these little pins here. These pins then interface directly to the chips that you see here, the chipset on the board, on the CPU itself. And then that CPU sits inside of a socket. So I'm going to slow down a little bit because I think I might be talking a little too quick. I get excited about this stuff. I can't help it. So let me just slow it down a notch. So now within the CPU itself, we have an arithmetic logic unit. This is the piece of the CPU that is going to do and perform the mathematical calculations. We then have the control unit. And what the control unit is going to do is it's going to regulate the instructions that are being sent to the ALU. Think of it as like kind of a staging, right? A line queue. It's got all these commands coming in and it's queuing them up and then it's placing them into the ALU as appropriate. So that's what it does. The control unit is the traffic control, if you will, for the arithmetic logic unit that's actually doing the hard work of the CPU and processing information. The central processing unit has a fetch and execute process. Again, orange, pay close attention, memorize these things. The process takes 4 steps for a single CPU cycle. And these 4 steps are to first fetch the instructions. So we get that from the memory. What am I supposed to be doing? Then the control unit's going to decode those instructions. It's going to make it ready for the processor to process them. Then it's going to execute. It's going to actually perform the mathematics on those instructions. And then it's going to store those results or outputs back into the RAM, back into the memory. And that would be a write. So again, fetch, decode, execute, write. Memorize that as best as you can. Now, pipelining. Pipelining is an interesting concept. What it's doing is combining multiple steps into a single combined process. So it is simultaneously fetching, decoding, executing, and writing. And it's doing that in a single action. And each part of those steps is referred to as a pipeline stage. Let's take a look at what that looks like. So a non-pipelined, we fetch, we decode, we execute, we write. We fetch, we decode, we execute, we write, so on and so forth. Repeat, repeat. Now, when we pipeline it, we do all of that in a single failed swoop. So we've done our fetch, our decode, our execute, and our write, and then on and on and on. So it is, it's a more efficient way to move instructions through the CPU. Now, the CPU is very busy, and so it needs to be interrupted. In order to get it to process a new instruction, it has to save its current task, its current state, and it needs to pause that and process a new request. Once the interrupt task has been completed, the CPU picks up where it left off. Similar to when those of us are working from home and our children or spouses interrupt our Zoom calls. We pause what we're doing, we handle that situation, and then we go back to where we were. And interrupts are generally hardware related. So this is going to be something like, hey, there's a mouse action, or there's some other type of physical activity, if you will, it's happening that involves the hardware. And so it's going to interrupt. And I noticed the chat's a little quiet tonight. I hope that's because you guys are like engaged and paying attention, and that I'm not just boring you to death with this stuff. So feel free to let everybody know how it's going. We love feedback. So here's a graphic that's going to show you how this input-output controller, this interrupts, how this is working. So for example, the I/O controller here is interfacing with the CPU. And then maybe there's a keyboard action that I need to take. Maybe I need to click open a new window. So it's going to hand that off to the interrupt. That's going to tell the CPU, hey, process these instructions first. And then when it's done processing those instructions, it will then return to its normal state of processing what was previously being run. Okay, and down here you see the network interface to the network cable. The central processing unit has a process. Now, process in this context means an executable program, and its data is loaded and running in memory. So the program executable is running, it's a process, and it has data loaded into the memory. A thread, which is also called a lightweight process or LWP, is a child process where one process has spawned another process. A heavyweight process, for example, in HWP, is called a task. One big advantage for threads is they can share memory. This is the part you need to remember. Threads have the ability to share memory. Process states are new. That's a process that's being created. Ready, a process is waiting to be executed by the CPU. Running, a process is being executed by the CPU. Blocked, it's waiting for the interrupt controller. Or terminate, a process has completed. Now, a zombie or orphan process or thread is where the parent has been terminated, but the child process has not. Multitasking, something that we all say we're good at, but we're all actually bad at. However, the CPU is incredibly good at multitasking. And so it allows for multiple tasks or heavyweight processes to run simultaneously on a single CPU. Multiprocessing allows for multiple processes to run on a single CPU. And remember from the previous slide, a process and a task are different. But the nice thing is the processor can handle both. Now there is symmetric multiprocessing or SMP. Well, that's one operating system to manage all CPUs. And there's asymmetric multiprocessing or AMP, and that's one operating system image per CPU. Multi-programming are multiple programs running simultaneously on a single CPU. Most of us have that today if we're running any modern operating system. And multi-threading allows for multiple threads or lightweight processes to run simultaneously on a single CPU. Most of us have this in our PCs today. Now there are watchdog timers, and watchdog timers are designed to recover a system by rebooting after a critical process has hung or crashed. There's a complex instruction set computer or a CISSP. Or a reduced instruction set computer, an RISC. So here you can see that there's 3 stages to a watchdog timer. Timer stage 1 is it gets kicked, so it's activated, and it has a timeout threshold. And when that threshold is achieved, it either triggers a corrective action or it triggers another timer at a more advanced stage, in this case, stage 2. And same thing there, it hits its timeout threshold and it either triggers a corrective action or it enables another timer, in which case, if that timer times out, it goes back and it actually kicks a reset on the computer itself. Blue screen of death is what you're probably most familiar with. Now we have memory, and memory needs addressing. So the way that we make heads and tails out of memory locations is by using addresses. And there are direct addresses. So add an X to the value stored in the memory location #YYYYY. Why are we covering this? Because it's very important. There are indirect addressing modes. So it works very similar to direct. However, the memory address is actually in a different physical location, not the location itself. There's the register direct. So it's going to reference the CPU cache register, not the secondary memory. And a register indirect, it's going to reference the CPU cache register as well. let's take a look at what that looks like. So direct, so we want to add X here. So we directly add it. Now indirectly, we see here that Y actually routes to Z. So this is sending it to another physical memory location, but the call is going to this memory location. Register direct, again, just straight to that register. And register indirect, again, it passes it through a secondary address space before it actually touches the physical location. Indirect addressing, here's another example of it. RAM locations 3001, the data elements 5002. We push that up to a vector table, which then passes that down. So location 1 or location 3001 holds the address of the item within the vector table, which is location 5002. The location of the vector table contains the address of the data to be fetched. The data is fetched from location 9000. Wrap your head around this stuff. I don't think you're going to be quizzed on this specific piece, but you will be quizzed on direct, indirect, register direct, and register indirect. Memory protection. So this is preventing processes from accessing memory space that are currently assigned to another process or thread. Memory protection is required if you have multiple users and or multitasking systems. So you really want to protect that memory space. Hardware segmentation, this is having completely separate hardware. And virtual memory. Virtual memory is virtual addresses mapped between applications and hardware memory. Swapping and paging. So swapping and paging is using virtual memory to copy the contents into a primary memory or RAM location to or from a secondary memory. So not directly addressable by the CPU on disk, right? So this is, again, we're using that virtual memory. We're doing some paging. Kernel accessing memory in the swap space results in a page fault. So if the kernel attempts to access memory in a swap, it's actually going to cause an error, and that will result in a page fault. BIOS, basic input-output system. I would normally, if we were in person, say quick show of hands who's ever logged into their BIOS, but we're online, so that doesn't work. But what BIOS basically is the firmware that it's the very first piece of computer code that the computer runs when it's booting up. It loads this prior to the operating system. So when you first boot up that computer and you see the black screen and some white text, and it goes boop, and it does the memory test, right? Maybe it's a long test or a short test, but that's called the power on self test, or post. Post then finds the boot sector. So that's the piece of the hard drive that has the instructions for starting the operating system, and begins to fire off the OS kernel. The kernel loads and then executes into the operating system. So remember, kernel below, OS above. This is what BIOS looks like if you've never been in it before. They've gotten a lot more attractive and mouse-driven in the modern era, but this is what most of us grew up on. And so that's BIOS. Take a drink here. Any questions? Let the moderators know. All right. So BIOS is what happens when the PC is turned on. The BIOS initializes the hardware. The BIOS then calls the master boot record, which almost usually always is stored at the start of disk 0. The master boot record then loads the code from the boot sector of the active partition, and then the boot loader is run from the boot sector. So the boot sector loads and runs the bootloader from the file system. In general, the master boot record consists of 512 or more bytes located in the first sector of the drive. In general, there are times when that's not true, but most cases it is. Then we have worm storage. So this concept is write once, read many. Generally going to be used for record retention and high integrity information. CDRs, DVDRs are considered write once, read many. Rewritable CDs and rewritable DVDs are not. And I don't know how many of us are still using these days, but it's an important concept because you will be tested on it. Then we have the Trusted Platform Module, or TPM. This was developed and updated by the Trusted Computing Group. It is an international standard. The processor provides additional security capabilities in the form of hardware. It's usually located on the motherboard itself. However, I have seen it where it's a card that is added on. It is hardware based, so it does hardware based encryption, which means it's able to do the encryption processing very quickly. It provides boot integrity, so it prevents rootkits and kernel bypass attacks. It allows for platform integrity and disk encryption. These are the primary uses for TPM, and it has grown in popularity. Here's an example of when it's not actually part of the board. So sometimes it's a chip like this, and sometimes it's an add-on like that. Most modern machines, it's going to be embedded directly into the board. All right, so a quick tidbit. The DoD specifies new computer assets as having, must include TPM 1, 2, or higher where required. So if you're working with any of those agencies, and this information is a little bit older, but it's still very applicable, and they do require TPM. The banking industry now also requires TPM. All right, data execution prevention and address space layout randomization. Wow, that's a mouthful. It is the intentionally corrupting the memory of a system via, for example, a stack or heap-based buffer overflow condition. It is a common means employed by an adversary. So buffer overflow is one of the very first attacks I ever did. And unfortunately, it is still an effective attack. There's still plenty of software out in the market today that haven't accounted for this. And so you can actually blow the heap or the stack by overflowing the buffer. It is enabled within hardware and or software and attempts to ensure that the memory locations are not predefined to contain executable content, will not have the ability to have the code executed. So that's the randomization piece. Here's an example of what a buffer overflow would look like. So this is a normal stack. This is the top of the memory. This is the bottom of memory. We fill from the bottom to the top. If the stack is smashed, you can see here that we're now able to insert a new pointer. So this is us. If the bad guys or gals are doing this, this is how they're getting their code executed. They're actually overflowing the buffer and then inserting their pointer to a memory address that has the code they wish to have executed. You can go to this here and it'll break it down even further for you. The kernel. Oops, let's go back, jumping ahead here. All right, the kernel, which is the heart or core of the operating system, is usually running at ring 0. It is the interface between the operating system and hardware. And primarily, there are two types of kernels. There's the monolithic kernel. So that's compiled into one static executable, and the entire kernel runs in supervisor mode. It requires recompiling to add any new features. And then there's a microkernel, and this is a modular kernel that can add functionality via loadable kernel modules. You'll see that mostly in Linux. The reference monitor is a core function of the kernel, and it mediates all access between subjects and objects. It is always enabled, and it cannot be bypassed. So you can see here the subjects, objects, our audit trail, and our authorization database, and the reference monitor lives in the middle, handling that coordination. User and file permissions, also quite important. So Linux and Unix permissions have an output of Linux ls-la/etc. And you can see here the owner, the group, and the world. So these are the permissions that they have. So you can see read, write, execute, read and execute, read and execute. So you can see here, this is a little bit of a different view, but that's what those letters indicate as what the permission level is, read, write, and or execute. Users and file permissions, types of permissions that are available depend on the file system being used. In Microsoft NTFS, the file permissions are read, write, read and execute, modify, and full control. Full control is read, write, execute, modify, and in addition, the ability to change the permissions. Okay, and here's an example of what that looks like. If you've ever been in Windows, this is probably quite familiar to you. So that's that. Now, virtualization. Virtualization is adding a software layer between the operating system and the computer hardware. Multiple guest systems can run on one physical host. So you have one physical host and many guest operating systems. And there's a couple different types of virtualization. So there's transparent or full virtualization. This runs the stock operating system and no changes to the operating system are necessary. And then there's para-virtualization, and that's specifically modifying the operating system or modified kernel. So when it's doing its virtualization work, that's where it's doing it. Transparent full virtualization, which is the most common, runs the stock OS and you don't have to make any modifications. Here's an example of full versus para-virtualization. Boy, it's been a day. You have your host computer and system hardware here, ring 0. So this is your virtual machine here. Here's your guest operation at guest OS at ring 1 and user apps up at ring 3. And in the para-virtualization, you can see there's this virtualization layer here, which then goes up to the guest OS, and then your user apps are at ring 3. So unlike full virtualization, para-virtualization involves modifying the operating system kernel. That's the part you need to know and remember that. Now the hypervisor is the software that controls access between the guest operating system and the host hardware. A lot of us are familiar with VMware or Hyper-V. These are the hypervisors that allow for that control access between the guest OS and the host hardware. Type 1 is part of the operating system and it runs on the host hardware, so VMware ESX. Type 2 runs as an application within the operating system. The most common version of this is a VMware workstation. And again, another visual example for you where applications, guest OS, here's the hypervisor down, type 1 hypervisor, hardware memories below. Here is a type 2. You notice that it runs above the native operating system. The applications are to the side of it. And then there's a guest OS and applications that run within the VM. And it's running in the native OS instead of on the hypervisor itself. Some of the benefits to virtualization and distributed computing. There's a lower hardware cost. There's I'll slow it down. Anything I should go back and recover. I'm getting a notice from the moderators here, and I'm happy to go back and recover some things if we need. Wait a minute here. I'll have a sip of water while we see what they say. So the benefits of virtualization are going to be a lower hardware cost. You're able to reuse hardware. By reusing the hardware, it lowers the need to have a bunch of extra hardware. It generally reduces your power cost because you're able to, again, use that singular piece of hardware and not have to have multiple machines plugged in. It's going to have a physically smaller footprint in your data center. Because you don't have to have racks and racks. You can have one host run many guests. It does have some considerations for security, though. It does introduce layers of complexity. And as we learned earlier, complexity is the enemy of security. So as we add complexity, we have to take time to think about the impact of that. But it is very easy to bring up new systems. Now that has a benefit of, great, on the admin side, I can bring it up quick, but on the security side, that new system could be spun up without the proper checks and balances in place. So that's why it's a security concern. And any issue that the host experiences, so if the host has a hardware failure, it will affect all the other guests, all the guest OSs on that piece of hardware. And so, you want to be thoughtful. I ran into an example once in my career where they had virtualized the primary, weren't able to bring things back up because the primary domain controller was a virtual guest on the host, and the host kept attempting to join a domain that did not yet exist. So be thoughtful, planful if you're responsible for designing any of those systems. And I would not ever host systems with varying security sensitivities within the same hardware. So if I have a very highly sensitive system, I'm probably going to keep it physically separate, different hardware, from a low sensitivity system. And this is, again, just to mitigate risk and reduce the likelihood that something could happen. Cloud computing. So as we know, the cloud is that place where magic happens. And the only risk in cloud is if the data gets wet. I kid. Cloud computing is just a computer in somebody else's data center. So I just want to level set that first. But it does give us a ton of advantages. So it allows us to leverage economies of scale. It provides us with things like infrastructure as a service. So this is where the customer configures the operating system and everything, and everything else. So like Linux server hosting, different kind of pre-made infrastructure, if you will. Then there's platform as a service, or PaaS. Now this is where you get a pre-configured operating system, and the customer installs and configures everything else: the web services, the hosting, the network pad, or just all those various things. But it kind of comes pre-configured. The most common flavor of platform as a service on the Microsoft world is the SQL Azure service. A lot of people using that today. Then you have software as a service. And this is what Security Studio does. We're a software as a service company. We provide a risk assessment platform that is delivered via software as a service. And that means that we take care of everything for you. You just use it and consume it. There's no configurations. You don't have to worry about backups, any of that stuff. So software as a service, very popular these days. Then you have private cloud. And a private cloud is dedicated to a single customer. Do that. Sometimes it's referred to as a VPC, or a virtual cloud is shared amongst multiple organizations. So if you go to AWS or Amazon and you just stand up services and you haven't put them into a private cloud, then you're operating in the public cloud. And your resources could be running on physical hardware that is shared by many, many, many other organizations. So let's take another look at that. So IaaS, virtual machines, servers, storage, load balancers, network components. Platform as a service. These are the executable runtime databases, web servers, development tools. Maybe it's Visual Studio as a service. And then you have SaaS, and this is going to be things like Salesforce, so your CRM, email, virtual desktops, games, various things like that. It's an application layer. And then there's the cloud clients, and these are the web browsers, mobile apps, thin clients, terminals, emulators, things like that. Cloud computing has its own considerations for security issues. When we run to the cloud, we a lot of times think somebody else has it. The best bit of security advice I can give you, and this isn't in the book, but it should be, is treat the cloud to the same security standard as if you ran it internally, and then add a little extra. You're really putting a lot of trust in a provider to provide you these services, and there's some considerations. And one of those is you need really, really strict service level agreements. You need to be incredibly clear on what is and is not acceptable within timeframes, who's responsible for what. You're going to have limited visibility because it's not your data center, it's someone else's. And limited visibility can cause its own set of issues. The cloud is going to have a shared infrastructure and shared targets. So again, you could have multiple companies' data running inside of your environment. You need to advocate for the right to audit and the right to assess and the right to test. You actually have to ask for these things. They're not automatics. You have to make this part of your agreements and contracts. And most of the big cloud providers have mechanisms for this today, but you have to know to do this. And then, there's the consideration of geo location. Where is the data geographically located? So, for example, if you are a European citizen, you are subject to the General Data Protection Regulation, GDPR, and that pretty clearly states that European data needs to stay in Europe, and if it doesn't, wherever it is must follow the same standard. So most companies choose just to keep the data localized. Or in the case of working with a government, if you work with the US government, they love their data to stay inside the US. When you're using a cloud provider, you have to account for that. You have to think about that, and you have to configure that. Grid computing is another type of distributed computing. You guys maybe remember SETI. SETI had this cool thing years ago where you could install the app and use your idle CPU cycles to help search for intelligent life. This was one of the first examples that I personally became aware of for grid computing, and it was pretty cool. There's a thing called BOINC, and it's an open source software for volunteer computing. So this is where you donate your CPU cycles to help calculate different things for scientists, universities, companies. A lot of processing power out there in the world going unused, and grid computing allows you to take advantage of that. And you can get some serious throughput, right? Like 165 petaflops. So just to give you an idea, that's 165 times 10 to the power of 15. That is an enormous amount of information being processed there. Then we have peer-to-peer. If you ever downloaded anything from LimeWire, Napster, any of those sites back in the day, those are peer-to-peer sites. And in in a peer-to-peer relationship, any system can act as a client and as a server or both. Peer-to-peer is decentralized and neutral. Napster, again, great example. They had central index servers, and then they got in trouble for that. Gnutella and BitTorrent did not. IP issues, data integrity issues, and data losses are all risks of using a peer-to-peer system. We have thin clients. These rely on central servers. The central server runs the application and stores the data. They generally have simplified security, and they're cheaper than full PCs. We have diskless workstations. I had to practice that a couple of times so it come out right. They contain CPU, memory, and firmware. There is no disk drive. The kernel and operating systems are loaded over the network, and it does a BIOS post, then it connects to the TCP IP, and then does a boot TP, which is typically a NIX or DHCP, which is more robust. Then we have thin client applications. These are going to be browser-based and allow you to access centralized applications and data. It's going to run on a full PC. The ones that we're most familiar with are going to be Citrix ICA and Open Thin Client. So if you've ever used a Citrix ICA solution, that was a thin client application. We have the Internet of Things, IoT, or as I call it, the Internet of Terror. But these are all these not so smart devices that we connect up in our homes. This is going to be our Roomba, Alexa, our TV if it's smart, surveillance cameras, home automation, the garage door opener that knows I'm coming before I get to the house. They are an absolute security nightmare. They were never designed or engineers didn't put any means or mechanism in place. Don't get patched. The customer support is awful. and features Trump security every day. Quick personal story. I have a sister-in-law who decided that as a matter of convenience, she wanted to put a camera in her child's bedroom so that when she was downstairs cooking dinner, she could keep an eye on her daughter. We since had a very deep and scary conversation, and she doesn't do that anymore. But that's IoT run wild. That's convenience without thinking about the impact of security. And as security professionals, as you get into businesses, you're going to interact with IoT that the business has introduced. You need to know IoT, security nightmare, incredibly hard to secure. Okay. Everybody's warning about it, including me. All right. So emanations. Emanations are something I do after too many tacos. But it's energy that escapes an electronic system. And why that matters is there's a type of attack called side channel attack. You can actually get a lot of information out of an emanation. Today, we're able to use lasers to listen to the vibrations of the glass on your window to pick up the typing of your keyboard. There are some really cool radio tools that you can use to actually listen to the modulation of the CPU itself and pull data out that way. But basically, any energy that's leaking from your system could be used to reconstruct data. Tempest is a National Security Agency specification and NATO certification referring to spying on information systems through leaking emanations. This includes unintentional radio or electrical signals, sounds, and vibrations. There are shielding standards, many of which are classified, but there are 3 levels that are public that you can shield from those emanations. Most common protection I've seen in the real world is a window film that certain agencies and businesses will place on the windows of the office to prevent any emanations from escaping the building. You can buy it, for those of you that are really into your privacy, you can buy it on Amazon. So, system vulnerabilities, threats, and countermeasures is the topic. Backdoors. Backdoors generally are going to be malicious. Now, I remember many gray hair ago that system admins would put in backdoors to make it easier to get in if they needed to, or in some cases, get in after they have been terminated. But they are usually malicious. And it's a system shortcut that's going to bypass the security checks. A lot of times, a backdoor is going to bypass the login, and it's also generally put in place as part of a larger attack profile. And then we have maintenance hooks. Maintenance hooks are usually innocent, and they're shortcuts installed on purpose by the system designer or programmers to help them, maintain the system. But they should never be left in any production system. They're okay to use if you're building up the system and it's in its test phase, but you got to remember to go back and take them out. All too often they get left behind, and that ends up becoming the attack vector. Malware or malicious software or malicious code. Zero-day exploit is a type of malware where a vendor has not yet released a patch or a fix for the flaw. That's why we call them 0 days. Just an interesting thing to note, 0-day exploits are not able to be detected by anti-malware or antivirus solutions, as no one has seen them before. So there's no signature associated with them. A computer virus typically does not spread on its own. They come in various flavors and types. I can share with you that Evan's first job in the information security world was cleaning boot sector viruses off of Windows 3 machines. But they come in different forms. One of them is a macro virus. Then you have boot sector viruses. stealth viruses, polymorphic viruses, and multi-parte viruses. General rule of thumb here is viruses embed and worms spread. So worms, which is another type of malicious code, self-propagate. They are able to spread from one machine to another machine. Damages include malicious code, wasted resources, usually network related. And some of the most famous worms include the Morris worm, I Love You, Nimda, Code Red, and Melissa. I remember living through I Love You. That one was not a lot of fun. And remember, everyone, keep it respectful in the chat. Just want to make sure we're doing that because we're all adults here and a lot of folks are sacrificing to make this happen. So, all right, here we go. So here's a couple of examples. So this is the Love You worm. Okay, here came in, and this is old stuff. I don't know when the last time my Outlook looked like that, but it's been some years. And this is a common ransomware that you will see if you do get ransomware. That's going to pop up. If you see that and you don't know what to do, this is the time to call for help. Call my friends over at FRSecure. They'll come clean this mess up for you. Trojans. So Trojans, we know this from the Troy, I believe. But one function is benign. So a Trojan is always masked. It's going to give you what you thought you were going to get. You downloaded a game, you downloaded a calculator app, you downloaded a word processing app. And in addition to doing that, it's also doing something else. And almost always that second function is malicious, whatever it is, but it's generally malicious. Some of the famous Trojans include Zeus Trojan, CryptoLocker, NetBus, Back Orifice, Shadun, which is an Android Trojan. And one of the most famous Trojans was the Trojan War, where they actually used a Trojan horse. And so here the horse was supposed to be a gift. They accepted the gift. They brought it inside the city, inside the perimeter of the walls of the city. And then inside the horse were a bunch of soldiers who then came out and attacked everyone. So same concept, just delivered digitally. Rootkits. Rootkits replace a portion of the kernel and or the operating system. Usually they're going to be operating in user mode or in ring 3, referred to as userland. And the kernel mode, again, is ring 0. So remember those rings from earlier. It's important. It comes up often. Common rootkitted binaries are LSPS and many, many others. You can Google, there's lots of interesting stuff out there about rootkits. Antivirus software, it's going to be signature based. So back to something I said just a little bit ago about 0 days. The reason that 0 days are so effective is that we have not yet developed a signature for it. The way antivirus software works is by comparing the signature of the code against a known database of signatures of code that has been found to be malicious. And this is why you have to keep your antivirus software up to date. What you're doing is you're updating those new signature files, okay? But they also can do heuristic based or anomaly and behavior based. So some of the newer stuff is looking for unusual patterns of behavior in the code. Different anomalies, like, it claims to be a Microsoft Word file, but yet it's trying to act as a web server. These are the types of things that would trigger a heuristic based antivirus to take notice and push an alert to you. Let's see, server side attacks or service side attacks. So this is where you attack a service. And then we have client side attacks, which are basically downloads. So this is, here we have a vulnerable client. It makes a request to the malicious server. The server then sends the malware back to the client. And then here we have the client actually attempting to connect to their own legitimate server, but the attacker has launched a malicious attack in the middle. So the attacker is reading the TLS connection and then redirecting the probes to the server. All right, I'm gonna pause for a second, give folks a chance to catch up. Any questions, moderators? All right, seems like we're doing pretty good here. Not a lot of questions. I hope that's a good sign. Let's talk about web architecture and attacks. So OWASP is the most common open web application security programming is what OWASP is, and they publish a top 10 most critical web application security risk. I may have got the acronym wrong, come to think of it. No, maybe I got it right. I don't know. I'm getting tired. I'm sure you guys are too. So the OWASP top 10, basically they have produced a top 10 list of the most common types of attacks. And this was the list in 2013. And this is the list. It says 2017, but I checked. It is also 2021. Yeah, on the previous slide, that was a man-in-the-middle attack. Yes, where the little man had intercepted the TLS connection. That's a man-in-the-middle attack. So not much has changed, unfortunately. Injection is still the number one. Broken authentication, number two. You can see here they actually combined a few to make it a little bit simpler. But this list is the same list today as it was in 2017, and it's not much different from the list in 2013. So it's important to know this because these are really the top risks that we are defending against, that we're protecting against. So just remember that. So it's broken authentication, sensitive data exposure, XML external entities or XXE, broken access control, security misconfiguration, cross-site scripting, insecure deserialization, using components with known vulnerabilities. I've seen that far too many times in my life, and insufficient logging and monitoring. So when you're trying to protect against these web apps, when you're trying to protect against systems, it's important to know, these are the most common threats. These are the most common areas where we need to do a better job of securing and hardening the code that we run and the applications that we use. All right, so applets. Applets are going to be, gosh, I haven't seen an applet in forever, but small pieces of mobile code that are embedded in other software such as web browsers. They're going to be downloaded from the servers and they're going to run locally. Java is a type of programming language. It is an object-oriented type of language, and it's in bytecode, so it is platform independent. And because of that, in order to execute Java, you must run the Java virtual machine or JVM. The Java virtual machine, and as we learned earlier, virtualization, right? A JVM is going to be a type 2 virtualization because it's running above the operating system. And it's going to allow you to then translate that Java code into whatever your native OS platform code is. Applets run in a sandbox. They tend to be sandboxed. Again, it's orange. Pay attention to that. Applets run in sandboxes. ActiveX. And this is one of these things where some of these things are falling out of favor. You will still find them in some legacy systems, but it's important to know it for the exam. They will test you on this. ActiveX was Microsoft's attempt at Java. It didn't really go so great. It worked all right, but it was a security nightmare. Their functionality is very similar to Java applets, but they only work on Microsoft systems. and they use digital certificates for security. So recap, applets run in a sandbox. ActiveX uses digital certificates for security. That's what you need to know from this one. XML, so extensible markup language. It defines a set of rules for encoding documents in a format that is both human readable and machine readable. XML documents should always begin by declaring some type of information about them. So if you ever open up an XML document, up at the top, it's going to say XML doc type this. It's then going to maybe have a couple of tags to describe what it's doing. Then you have SOA or SOA, service-oriented architecture. This is an architectural pattern in computer software design in which the application components provide services to other components via a communication protocol, generally done over a network. The service can be used and reused throughout the organization rather than built within each individual application. SOA concepts include SOAP, REST, DCOM, Corba, and others. The one I've run into most common is REST and SOAP, but there are other flavors out there. All right, polyinstantiation. This is your $15 word of the class, polyinstantiation. So what polyinstantiation is two different objects or instances of objects that have the same name. If you open up multiple copies of Microsoft Word, you go in your task viewer, you're going to see multiple objects of Microsoft Word exe or Word exe, but those are polyinstantiated instances of Word. Depending on the security level established, one record may contain sensitive information and the other one does not. And that is, a user will see the record's information depending on his, her, they, them, other level of confidentiality dictated by the policy. So that's important to understand. The policy dictates the confidentiality, and you can have multiple objects with the same name running at different levels of sensitivity. It also provides for the ability of a database to maintain multiple records with the same key, and it is used to prevent inference attacks. Inference requires deduction by using clues, and some of the controls might be polyinstantiation or diffusion. Aggregation is a mathematical process that asks every question. In aggregation, there is no deduction. And the control here may be to limit the number of queries against the database. We have data mining, and this is going to be searching through many, many terabytes of data, yottabytes, petabytes, all the bytes, bytes. The data it's stored, and what it's doing is it's looking for patterns. So it's trying to find patterns while crawling through and searching through this vast volume of data. Generally, it's used extensively for detecting fraud. So again, they're doing pattern detection to try to find patterns that indicate fraud. Sometimes it causes a privacy concern if the data has not been properly anonymized. So data mining, right? Digging through the data, trying to figure out, Google, good example here is Google does data mining on my search history. And they're not very good at it because they keep trying to sell me stuff I just bought. I'm constantly getting ads for a dishwasher that I bought last week. They need to get a little better at their predictive analytics and start selling me stuff when I'm searching for it, not after I bought it. But data analytics is often used to determine a baseline of normal behaviors. So any deviation from the baseline of normal behaviors may indicate misuse or compromise. When we talk about user behavior analytics we're talking about data analytics. We're talking about looking at the user's data to determine a baseline of normal behavior. And what we're alerting on is any deviation from that baseline that may be an indicator of misuse or compromise. Defense in depth. Defense in depth is a concept where the shell is crunchy and the center is gooey. This is not good. We don't want a crunchy shell and a gooey center. The whole idea of perimeter-based security is rooted in this crunchy shell and gooey center. As long as it's outside the firewall, I'm fine. This is bad news bears. We want to avoid that. Network segmentation and isolation, very important. This is making sure that I've got the appropriate separation between my networks, keeping my sensitive data separate on a different VLAN or network isolation from, say, my publicly available data or my Discord server, right? I'm going to want to keep that separate from my healthcare server. The NSA has a methodology for adversary obstruction. This is the link to it. Feel free to check that out. Then there's the mobile device defenses. Most common here is the mobile device management, or MDM. This is the ability for an organization to manage the mobile devices that are there. They can remote service those devices. They can remote wipe data from those devices. MDM is how that gets done. We also have network access controls, or NACs, that we can use to do mobile device defense. 8021X certificates, authentication, remote wipe, and encryption. These are the kind of things that a mobile device management solution and mobile device defenses allow us to do. All right, I'm going to take just a quick break before we get into this topic. Any questions from anybody on the chat? Steve had asked about the OWASP. OWASP will be mentioned. The list itself is not testable as best as I recall. So I have another joke for you. Two SQL statements walk into a bar and see two tables. The SQL statement walks up and says, "May I join you?" I'll tell you another really bad SQL joke. SQL statement walks into a bar, sees two tables, walks up and says, "Want to join the union?" Really bad, I know, terrible. All right, encryption. Woo, encryption. Okay, a lot of orange on this. I'm going to go through the key terms. Don't worry, we will be done soon. We're nearing the finish line. We might even finish a little early tonight. Yay. Key terms, though. Cryptology. Cryptology is the science of secured communications. Cryptography is creating messages whose meaning is hidden. Cryptanalysis is the science of breaking encrypted messages, recovering their meaning. Cryptology encompasses both cryptography and cryptanalysis. A cipher is a cryptographic algorithm. Passwords are ciphers, right? Plain text is an unencrypted message. So that's what you see on the screen now is plain text. Ciphertext is an encrypted message. And so when you look at it, your human eyes can see it, but it doesn't make any sense. Encryption is what converts the plain text to a ciphertext, and decryption turns a ciphertext back into a plain text. So to encrypt, we're converting plain text to ciphertext. Decryption is turning ciphertext back into plain text. I'll leave that sit there for a second so you can try to lock that away in your brain. Confusion, diffusion, substitution, and permutation. This is your other $10 word. Confusion means you've been sitting through this class tonight. No, I kid. Confusion means that the relationship between the plain text and ciphertext should be as confused or random. Cryptology was listed twice, two different definitions. The first definition was to say specifically to what it was, and the second definition, I want to go back and recover that just so we're clear. So here, cryptography or cryptology is the science of secure communications. Good Lord, slide deck, go back. Where here, this is just letting you know that it also encompasses, so in addition to being the science of secure communications, it also encompasses both cryptography and cryptanalysis. So yes, it shows up twice, but the reason for that is to show you that it's the science of secure communications and that science encompasses both cryptography and cryptanalysis. That can be a little confusing at times because confusion, right? So the idea is we want to make it as random and confusing as possible. This makes it harder for people to figure out what the heck is going on. Diffusion means the order of the plain text should be diffused or dispersed in the ciphertext. So it becomes, again, more difficult to figure out what's going on. All of this is done to increase the level of difficulty for someone to figure out what the actual secret message is. Substitution replaces one character for another, and this provides diffusion. So diffusion can be achieved through substitution. And permutation, also referred to as transposition, provides confusion by rearranging the characters of plain text anagram style. Is anyone else confused? Because this is confusing, right? The important part here is to really remember these definitions, study it thoroughly. Substitution and permutation are often combined. Unless you intend to have a career in cryptography, once you take the test, you can forget this stuff, right? But for the test, you really do need to know it. So again, those flashcards that I talked about at the very beginning of class, super helpful. Use them. Strong encryption destroys patterns. So any signs of non-randomness may be used as clues by a cryptoanalysis, hinting at the underlying order of the original plain text or key. So the job of a cryptanalysis is to try to unwind and figure out what the heck this secret message is. So any patterns that exist because the encryption was not strong enough, did not use enough confusion or diffusion or substitution or permutation, makes it just much easier for the cryptanalyst to break the code. Oh, an example. Gosh, you guys are hitting me hard on this one. An example of permutation. So if we rearrange anagram style, let me see if I can find something real quick, give you guys a quick example. And that's good to know. We should probably add an example of that to the slide. I am not a encryption master. This is some of the stuff I forgot after I passed the test. So just so you guys know, right? Some of this you have to remember and then forget. Let me see if I can find a visual for this that's going to be helpful because most of it is just really complicated math. Yeah, there's not really a good way to, here we go. All right, let's see, tab, let's take a look at this here. So if it'll load, come on. There we go. So as you can see, these are 24 unique permutations, right? So there's no repetition. So this is the original source. This is after it's gone through its first, second, third. Really, it's just really super fancy math. This is the best example I could find that did not involve a ton of mathematics, and I will be the first to admit that advanced discrete mathematics is not my strong suit. All right, next. All right, cryptographic strength. Good encryption is strong for key-based encryption, and it should be very difficult, ideally impossible, to convert a ciphertext back to a plain text without the key. The work factor, and again, orange, pay attention here, work factor, is going to describe how long it takes to break a crypto system, how long to brute force your way through it, in other words, decrypt without the key. So maybe you've seen the password strength chart before, where it says this password at 4 characters will take less than 5 seconds to break. This password at 11 characters will take approximately a day to break. This password at 14 characters will approximately take like 20 years to break. And those are all made up numbers, so don't anybody try to hold me to those. But basically, that's the work factor. The work factor is how long is it going to take to try every single combination and eventually just get lucky. The secrecy of the cryptographic algorithm does not provide strength, and this is Kirchhoff's principle. I cannot cite you Kirchhoff's principle off the top of my head, but I encourage you to memorize it and read it, and then like me, you can forget it after you learn it. Let's talk a little bit about some of the ciphers. So there's a monoalphabetic and polyalphabetic cipher. A monoalphabetic cipher uses one alphabet, a specific letter like E, and it's substituted for another letter like X. Monoalphabetic ciphers are susceptible to frequency analysis. So in this case, we're doing, this is ROT 13 here that we're using the method, and we've swapped A for N, B for O, C for this. Well, once you figure out that H equals U, now you're able to start to reverse your way back out of it. It becomes very easy. So you can actually look for frequency analysis in the letters in the English language. There are certain letters that occur more frequently than others, and we'll take a look at that in just a second. And because of that, it's actually very easy to find those repetition patterns. Because you know that particular letter is going to occur more often, you just look for that letter. And once you find that letter, it's a lot easier to start to figure out what the rest of the ciphertext might be. This wheel here is polyalphabetic, so it's using multiple alphabets. And so on one round, it might be A, and on the next round, it might be S. Okay, so let's take a look at frequency analysis. So E, believe it or not, most common, significantly most common letter. So if you can find E, a lot of times you can kind of reverse out and figure out. And just to refresh you, monoalphabetic ciphers are very susceptible to frequency analysis because of the fact that E in these letters exist at a higher rate of frequencies than others. Then we have the exclusive or XOR logic gate. Unencrypt the plain text, attack at dawn with the key of unicorn. So this is a fun exercise for you guys to do. A is binary of 1 0 or 0 1 0 0 0 0 0 1, and U's binary is 0 1 0 1 0 1 0 1. So this results in a ciphertext of 0 0 0 1 0 1 0 0 yada yada yada. That is character 20 in ASCII, and there's no text conversion. So this is a gate here. So you can see A is 0, B is 0 at A, and XOR AB is now 0. So this one, again, you don't really need to know this. I don't know why they put this in the book, but it's there. So let's do a little history lesson. Let's talk about the history of cryptography. Cryptography is the oldest domain in the common body of knowledge. It is literally thousands and thousands of years old. As long as people have wanted to keep secrets in written form, cryptography has existed. Egyptian hieroglyphics are a type of cryptography. They used pictorial writing. It was popular from roughly 2000 to 1000 BC. I am not fluent in Egyptian hieroglyphics, so for me, that is an incredibly effective deterrent. That's cryptography I can't break. I don't know how to read this stuff, right? And strangely enough, our children and the new generations, they're going back to using hieroglyphics. If you don't believe me, try to read one of their text messages, and it's nothing but emojis. So it's important to learn those ciphers too, but that's a different talk for another day. There's the Spartan cytale. So this was used in ancient Sparta around 400 BC, and it was a strip of parchment paper wrapped around a rod. The plain text was encrypted by writing lengthwise down the rod, and then the message was then unwound and sent. A rod of the same diameter was used to decrypt the message. And you see an example of that here. The Caesar cipher and other rotation ciphers. So there was a monoalphabetic rotation cipher that was used by Julius Caesar. Each letter was rotated. You would rotate the plain text letter forward 3 times to encrypt. So A first became D, and then B became E. This is where rot 3. So when we talk about rot, we're talking about rotations. The rotation can be anything you want. And a common rotation cipher currently used is rot 13. And it was, or I shouldn't say currently used, it shouldn't be used, but it was very commonly used, was rot 13, and that was used to conceal information on bulletin board servers such as Usenet. The Vingray cipher, I'm sure I pronounced that wrong, somebody can correct me, but it was a polyalphabetic cipher named after Blaise den Vingray. My French is terrible, and you would think with a last name like Cloutier, it wouldn't be, but it's awful. But he was a French cryptographer who lived during the 16th century. And his cipher has an alphabet that repeats 26 times to form a matrix called the Vingray square. And let's take a look at that. So here you are, you can see the various rotations. So we're talking about rot, so rot 0, and then 1, and then 2, and 3. And with each rotation, the encryption grows in strength. You can see the substitutions here. So X to A, Y to B, and this is the square we were just talking about. So you would find your message within that, 26 repeating alphabets within inside. Then there's the cipher disk. These are 2 concentric disks. Each have an alphabet around the peripheral. They both allow monoalphabetic and polyalphabetic encryption. For the monoalphabetic encryption, 2 parties would agree on a fixed offset, so set S to D. For polyalphabetic encryption, the parties agreed on a fixed starting offset and then turn the wheel once every X number of characters to set S to D, and then they turn their inner disk 1 character to the right after every 10 characters of encryption. This was invented in 1466 or 67, no one really knows, by Leon Battista Alberti. Alberti is considered the inventor of the polyalphabetic cipher, and it was used for hundreds of years up to and including throughout the Civil War. And believe it or not, this history stuff does actually matter. I know you're not seeing much orange, but it matters. The Jefferson disks, they were created by Thomas Jefferson in the 1790s. There's a picture of them here. 36 wooden disks. Each one had 26 letters in a random order along the edge. And the order of the disks was the cipher key. So the order in which you would load them onto the peg was the cipher key. Then there were book cipher and running key ciphers. These are well-known text, using well-known text as the basis for keys. So this is old-timey spycraft, where you would just pick a book, War and Peace, right? Pick War and Peace up, or better yet, pick up Evan's book on security, and then use that book. Using chapter, page number, chapter number, line number, and word offset, you would then figure out how you want to encode. So Benedict Arnold used a book cipher to communicate with the British. And here's an example of that. So we, attack at dawn, we the people. So A plus W equaled X. So the encrypted message is here. And then as you decrypt it, you find out it says attack at dawn, we the people. A running key cipher, instead of using whole words, uses modulus math to add letters to each other. So sorry, this is a running key cipher, not a book cipher. Book cipher would be actually using the book itself and then picking your substitution letters based on the page number, line, and word offset. Code books. Code books are assigned a code word for important people, locations, and terms. Now, an interesting thing to note, the only unbreakable encryption that exists to date is the one-time pad. It uses identical paired pads of random characters with a set amount of characters per page. When you get those one-time codes, it's based on the concept of the one-time pad. One page is used to encrypt the data. The same page at the receiver is used to decrypt the data, and then the pages are disregarded. Pages are never reused. If you reuse a page, then you've screwed up and it's no longer safe. But if you never reuse those pages, the one-time pad is the only mathematically proven secure form of encryption if the following conditions are met. The characters are truly random, the pads are kept secure, and no page is ever reused. Okay, so the one-time pad Vernam cipher was the first known use of a one-time pad. It was named after Gilbert Vernam, who was an employee of AT&T and Bell Laboratories. And the Vernam cipher used bits. Now, this is before the invention of the computer. And he basically copied and modeled off of other teletype systems. The one-time pad bits were also XORed to the plain text bits. So a very cool piece of technology, well ahead of its time. Project Verona was a project undertaken by the United States and United Kingdom cryptanalysis to break the KGB's encryption in the 1940s. And the KGB is the Soviet Union National Security Agency. The KGB used one-time pads for sensitive transmissions, which should have rendered the ciphertext unbreakable. However, they violated one of the three rules and they reused the pads. Many famous names were decrypted, including the details on the nuclear espionage committed by Ethel and Julius Rosenberg. Note, Project Verona itself is not testable. It is described to show the dangers of reusing the pages of a one-time pad. Now for some little bit more fun. These are great movies about cryptography. If you haven't seen The Imitation Game, it is fabulous. I really enjoyed it. It's Alan Turing, and it's about cracking the Enigma machine. It's actually a really good movie. U-571 is also about cracking the Enigma machine, but from the perspective of securing a machine to reverse engineer. And then All the Queen's Men, and this is a statistic. It's an interesting fact that we don't talk about much in our industry, but the original cryptographers were all women. The first computer programmer was a woman. So if you didn't know that, now you do. And it's amazing. Women have made such amazing contributions to this industry, and they definitely need to get more credit for it. There's the Herburn machines and Purple. These were classes of cryptographic devices known as the rotor machines. It was named after Edward Herburn. It looks like a large manual typewriter, and it's electrified with rotating motors. It was used after World War I through World War II, and in some cases into the 1950s. If you find one of these at a garage sale, snap that bad boy up and send me an email. The one we're probably all most familiar with is the Enigma machine. Again, you find one of these out in the wild, man, snap that thing up, let me know. But it was used by the German Axis powers during World War II. The cryptanalysis of Enigma was performed by French and Polish cryptanalysts. The work was then continued by the British, led by Alan Turing in Bletchley Park in England. Just to clarify for everybody, I know there's not much orange here. This stuff is testable. The history stuff is applicable. There's going to be several questions in the exam about various history things. So do try to remember as much of this as possible, because I don't know which one you're going to get, and you may get some, you may get none, but it could show up on your test. So it's important to know this stuff. The work was continued by the British. Enigma is going to be the big one on the exam. I remember that. I got hit with the Enigma question. Just be prepared. You might have to know some of this. So study it up. And then as soon as you take the test, you can forget it. But it was led by Alan Turing in Bletchley Park, England, and that's what the movie was about. The intelligence provided by the cryptanalyst of the Enigma, called Ultra, proved to be critical in the European theater of war in World War II. British cryptoanalyst Sir Henry Hinsel said the war, instead of finishing in 1945, would have ended in 1948 had the government code and cipher school not been able to read the Enigma ciphers and produce the Ultra intelligence. It looks like a very large typewriter with lamps and finger wheels. The military version of the Enigma, there were commercial versions that also existed, had 3 finger wheels that could be set to any number ranging from 1 to 26, and the finger wheels are what provided the key. As you typed on the keyboard, the finger wheels would turn and a lamp for the corresponding cipher text would illuminate. To decrypt, you would set the finger wheels back to their original position and type the cipher text into the keyboard. The lamps would then illuminate, showing the corresponding plain text. Just a few more to go. I know this stuff's getting a little dry. Sigma was a rotor machine used by the United States through World War II into the 1950s. It was more complex and based on the analysis of weaknesses in Enigma by the American cryptanalysts, including William Friedman. It was also called the Electronic Code Machine, or ECM Mark II. Very large, complex, and heavy. To date, it was never known to have been broken. Purple was the Japanese version of the Enigma machine, if you will. So the Allied name for the encryption device used by the Japanese Axis powers during World War II was Purple. It was a stepping switch device primarily built with phone switch hardware. Only fragments of the original machine exist. William Friedman led the United States effort against Purple. In 1942, the Allies decoded Purple transmissions, referencing a planned sneak attack on AF. The Allies believed AF was a code word for Midway Island, but they wanted to be sure. So they sent a bogus message, weakly encoded, stating that there was a water problem on Midway Island. 2 days later, the Allies decrypt a Purple transmission stating there was a water problem on AF. Whew, almost there. All right, the Wassenaar Agreement. After COCOM ended, it was created in 1996, and many more countries, including Russia, the former Soviet Union, Estonia, Russia Federation, Ukraine, and others, and it relaxed many of the restrictions on exporting cryptography. This is an important piece to know. The Wassenaar Agreement is one of the things you may be quizzed on, as well as some import and export regulations that we'll cover in later classes, but just know that it's a thing. All right, and I'm going to pause one more second for questions. Any questions from the group chat? Comments from the moderators? Interpretive dance moves? Recipes for delicious desserts? No? Moving on. All right, so with that, guess what? Oh God, we're done. Thank God. That's it. This is a lot. I didn't have to memorize this stuff. I just had to read it, and my brain hurts a little bit. So that's it tonight. I don't know how up to date this is. I'm gonna check with my moderators. Do we have class on Monday? I believe we are taking a break on Monday. Is that correct? Just waiting for confirmation here. You want to see dance? Do a little dance. Somebody confirm with me, because I do believe we're taking a break on Monday. And if so, when we pick it back up again, it's going to be more encryption. I am sorry, but not sorry. You have to learn it. It's one of those things. We should be at about page 160 in the book right now. So I have confirmed no class on Monday. Take a whiskey, take a night, just enjoy, relax, but don't sit on your laurels. Keep up with the study. It's important. And then come back with any questions. We will recap some of today's material, and we will cover some questions in the next class. I thank everyone for being here tonight and listening. Hopefully you learned something, and keep up the good work. Again, just a quick reminder, study in small increments, take breaks, get some exercise, get some fresh air, pick it up again. The longer you go with this stuff, the easier it is to forget it. So just again, small repeated increments will make life easy. And with that, I'm going to say good night to everyone, and I will stop video, but I will hold the slide up for just a few more minutes for everyone. Thank you guys. Appreciate you being here. Have a great night.